Hello, in this video I want to introduce the concept of integration in a conceptual way. In calculus you have two main concepts. You have the derivative and the integral. The derivative teaches you how to determine instantaneous rates of change, and the integral has a number of interpretations, but one of the major ones is total amount of change over an interval. So it's kind of like the derivative tells you how fast you're driving. The integral tells you how far you drove. That's kind of a good ballpark synopsis of integration. Like I said, integration has a number of conceptual interpretations. One of the most basic ones is the area under a curve. So let's just start with that and draw a couple pictures here. If you have a linear equation like that, and maybe a y-intercept of 4 and say an x-intercept of 3. If I asked you to find the area under the curve, that would be a very easy question, because the area under this curve is a triangle, and it would be 1/2 the base times the height. So easy enough. Unfortunately, most curves and most areas don't have nice geometric shapes that create them. So you have to get a little more creative. You know, we have shapes like the triangle, the rectangle, the circle, half circle that are at our disposal with formulas. But something like a parabola is not quite so simple. Say we have something like this, and I ask you to find the area under the curve, say from 0 to, say, 0 to 3. So you're looking at a shape that looks like this, a very irregular type of shape. So what you end up having to do is take rectangles and stick them into the space and approximate the area. So suppose we used 3 rectangles that are all a width of 1, and you did this. There's one rectangle. There's another rectangle. And there's a third rectangle. Obviously, you can tell that each rectangle has a width of 1. The height of the curve helps you see the height of each rectangle, which is different. And if you found the height here, and the height here, and the height here, and you saw the width is 1, the width is 1, the width is 1, you could add all these curves together and get an approximation for the area under that parabola, between the parabola and the x-axis. Notice there's error. We missed that region. We missed that region. We missed that region. This is an underestimate. And I'm just going to underline the estimate part. It is a guess. It is a guess. So in order to make that guess better, what you can do is have more rectangles. Perhaps instead of every one, here's my curve again. Say 1, 2, 3. Instead of every one, perhaps you have 6 rectangles that are all a half wide. This is not that great a picture, but you can see that there's smaller gaps at the top. So here, there's a gap, there's a gap, there's a gap, bigger gaps here. By adding more rectangles, you've got less space that's missed. And earlier I said that was an error. It's not, because I said we're looking at the space from 0 to 3, so excuse me on that. But still, we have error above the rectangles. It's still an underestimate, but we're getting better. So the conceptual solution is to add not just 3 rectangles, not just 6, but a lot. Hopefully, an infinite number of rectangles can be used to determine the area under a curve of any shape at all. Because the smaller the curve gets, the smaller the error gets, you could say as number of rectangles goes to infinity, the error goes to 0. So what we're going to do is we're going to use a limit, We're going to take the number of rectangles, and although we can't count an infinite number of rectangles, we can still work with the concept of an infinite number of rectangles using limits. And by doing that, we're going to end up with an error that approaches 0 and eventually will be 0. Let's continue with this concept. One other thing that I want to mention before we go too far, notice I've had the right corner of each rectangle touch the curve. This is a right-hand estimate, right-hand guess or solution. And if you had made the left corner touch, say you had done this, where you had left, like that. In this case, these rectangles that were previously under guesses, now they're over guesses. If you have a curve that is strictly increasing or strictly decreasing, a right-hand guess will be all an over guess or all an under guess, and then the left will be vice versa. Let me just draw an example of that for you real quickly before we continue. Let's draw a solely decreasing curve with a right-hand guess. You can see that these are all under guesses. They touch there and there and there and there, and we miss the region. We miss these little areas in the top. This is right hand, and then if you have left with a decreasing graph, you would have over guesses. And so forth. So there's left, 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 left. So all these now hang over the graph, and these are over guess, under guess. With an increasing function, something of this nature, a right guess is now an over guess. And again, with an increasing function, a left hand guess is an under guess. So this is something that you are often asked about on an AP test. It's very common. And I encourage you not to memorize, a decreasing function with the right guess is an under approximation, and vice versa with the left. It's easy to confuse yourself and to just not remember it correctly. So I recommend you draw a picture. Draw one of these 4 pictures if you need to determine if you have an under guess or an over guess. If you don't have a strictly increasing function, by the way, monotonic, only increasing or decreasing. That's what monotonic means. And also we're talking about monotonic over an interval. If you have a parabola, obviously a parabola goes down and then it comes up. But if you say you went from A to B, that would be this portion of the graph only. This parabola is monotonic. It's only increasing on that interval. Calculus is always a study of individual portions of the graph, either pieces or intervals. Derivatives look at individual points, and integrals look at individual intervals. So in this particular interval from A to B, even though I know the graph over here does decrease, we're only looking at the part right here, and it happens to be monotonic. It only increases. So keep that theme in mind as we go to integration. Just like derivatives, we studied the graph one point at a time. With integrals, we're studying it one interval at a time and looking at the behavior only on a certain interval. So from here, I want to go and just derive what an integral is, and kind of stick with the conceptual viewpoint for now. Okay. I'm going to write a formula at the top of the page, and then we'll talk about it as we get closer. So this is an integral sign right here, and these are the limits of integration, a to b. The left side of the interval is a, the right side is b. And we're going to integrate a function f of x. And let me write all this down, and then we'll talk through it. That's a sigma, that's a Riemann sum. I know this looks like a bunch of gibberish, but just bear with me for a minute. If you have a graph, we'll just do this this kind of graph right here, and say you have just call A and B here to be simple. If you let's see here. If you draw your little rectangles, you notice I'm drawing them a right-hand sum. This is designed for a right-hand sum. This formula is. We'd have to adjust it to be a left-hand sum. But I don't have that good of a picture. But imagine the widths are all the same here. Let me actually draw a little better one. That is 1, 2, 3, 4. We'll go like that. And this will be A, and this will be B. And again, we've got equal widths here. So that's my first rectangle. That's my second rectangle. That's my third rectangle. That's my fourth rectangle. So these are right-hand sums, just like that. We'll just get rid of that for now. The four rectangles are going to be named I1, I2, I3, and I4. And what's going to happen is with the sigma notation, that is just telling me you add up whatever is right here. So this represents the height of each rectangle, and this is the width. The width is going to be, if you take, so we got four rectangles here. If you went from A to B, and that was, say, 8, and you divide by 4, the width of each of those would be 2. If A to B was 4 and you divide by 4, the width is 1. If you subtract B minus A, this whole span, and divide by n, the number of rectangles, this is going to be the uniform width of every rectangle. So for starters, when you do integration in practice, it's essential that you pick widths that are uniform. In theory, yes, you could have any size you want, but if you want to do this in an automated efficient way, the widths all have to be the same. So B minus A over n is the uniform width. Start with that. Over here, if this is function f of x, just ignore all the rest here. If you put in the number a, so maybe this right here, if you want that height, if you put in a, and then you say plus I, which is 1 in this first case, 1 times the width, you start here and you add a width. That is the x value that you plug into function f that gives you that point, that height. So that tells you how high that first rectangle is. For rectangle 2, for I2, you have the starting point, which is A, and then you've got 1, 2 uniform widths. So that's going to be a 2 times B minus A over N, 2 over 2 widths. So you've got the starting place plus 2 widths, and that gives you a number that you plug into function f, and it gives you that point, which happens to be the height of that second rectangle. And then for the third and fourth, it works the same way. I is 3 here. This is the third rectangle, so you put in a 3 right here. 3 widths plus the starting point gives you the value that you put into the function, and it gives you that height, and it keeps going like this. So basically, you've got the uniform width times the individual height of each rectangle. So what you're doing here is you're getting the height and width multiplied of each rectangle. This right here is the area of each rectangle, this part right here. We go to sigma and we say start at 1 and go to rectangle n. So in this case, n is 4 because I had 4 rectangles. So you would, sigma means you add up the first one, you put in I as 1 and add up what you have, and then put in 2 and add that up, and then put in 3 and do it again. And you always start on that number, you end on that number. Since we're ending on at the number n, and then n is going to infinity, this is basically a way for me to express I'm adding up every individual rectangle, the area, height times width, and then I'm summing them all up. And by the way, there's an infinite number of them. And this is the same as an integral. So this is called the definition of an integral. This is how an integral is developed from scratch, from the concept of area. You've got a to b right here, the start of the interval to the end of the interval. And so with that, I'm going to just go ahead and apply this. And I will start with a very simple problem. I'll start with the linear equation that I just used a moment ago that we used. We had, what did I say, 4 and 3. And this was the function. It was, we went down 4 over 3 minus 4/3 x plus 4. That is that function. And I already figured out the area, so let me just write that down. It was 1/2 base times height, so that is 6. That's this area right here is an area of 6. So now we're going to use my formula up here. I'm going to set up my integral. The integral is from 0 to 3. The function is minus 4/3 x plus 6. We write a dx right there. I should have written a dx right there. We'll talk about that later. Bear with me for now. And this is going to be the limit as n goes to infinity. And we have sigma as I goes from 1 to n, just like we've got right there. And we're going to have f. A happens to be 0. B minus a over n is 3 minus 0, so 3 over n times I. And then the width, b minus a over n, is 3 over n. So we're going to continue to simplify this. We have this sigma. I goes from 1 to n. F of 3i over n times 3 over n. Over here, if I were to plug in 3i over n in for x, then we could figure that out. We could say on the side here, f of 3i over n is minus 4/3. I'll just kind of put a line here for a second, times 3i over n plus 4. The 3 cancel out. We get minus 4i over n plus 4. So this is going to go right here. So we're going to have this is going to be come down again and say equals limit and goes to infinity. Sigma as I goes from 1 to n, and we've got negative 4i over n plus 4 times 3 over n. Scoot that up a little bit. We're going to do some algebra here. Limit is n goes to infinity. Sigma as I goes from 1 to n. And then we've got 3 over n times minus 4i over n, distributive property, minus 12I over n squared. And then 4 times 3 makes 12 over n. Now we've got to do something with these sigmas. I'm going to break them up, and I'll show you how we deal with them. First, I want to just make a note here. This is just, by the way, there are some facts to tell you. If you have a sigma as I goes from 1 to n, and you're just adding up ones, 1 plus 1 plus 1 plus 1 plus 1, 5 times, then it equals 5. It equals n. So that's one fact. If you add up the numbers 1 plus 2 plus 3 plus 4 plus 5 up to n, that is n times n plus 1 over 2. And then there's a third one I'm going to tell you. I squared, if you go from 1 to n, is n times n plus 1 times 2n plus 1 over 6. So this is just for you to know and use. I'm not going to explain why at this point. You can show this. There's a proof method you can use to show that, but for right now we're just going to use it. So we're going to have limit as n goes to infinity still. We're going to do sigma for each of these. One thing about addition is you can break these up into 2 separate addition pieces. And keep in mind, I is the only thing that matters for the sigma. It doesn't care about the 12 or the n squared. So I'm going to bring that part out. Minus 12 over n squared times I. And then this 12 over n we're going to bring out also. And left over is just a 1. There's actually not an I there. So that's all we have remaining. And now I'm going to go to my formulas. I'm going to pick out that and pick out this here and here and reduce them to just n's. So we've got minus 12 over n squared times the sum of I is n times n plus 1 over 2 plus 12 over n. The sum of 1's all added up is just n. And that's now going to be the limit as n goes to infinity, minus 12 n squared minus 12n over 2n squared plus 12n over n. And that's going to end up being minus 12 over 2 plus 12, which is minus 6, plus 12, which is 6. So that matched the 6 that we got up earlier. And I know that seems like a lot of work, but I think it's very important that you learn how to not just use the tricks and shortcuts with integration, but actually do it from the definition from scratch. I want to do one more example like this. We'll start with my formula again, and this time I will use a quadratic equation. And I won't draw the picture this time. I don't think that's going to be necessary. But suppose you want to integrate. Again, we'll start with 0. We'll do maybe 0 to 5, and we'll do just how about x squared plus 3x plus 1. So we're going to just kind of go over here and set up my formula. N goes to infinity. Sigma goes from 1 to n. We have f of 0. The width is going to be 5 over n, so it's going to be 5 over n times I. 5i over n. B minus a over n is 5 over n. I need to know what f of 5i over n might be, so I'll just do that over here below. F of x was x squared plus 3x plus 1. So f of 5i over n is 25i squared over n squared plus 15i over n plus 1. That's going to go right here. That goes right there. I'm going to kind of box this off because that's not really part of the problem. We'll say this is limit as n goes to infinity. Sigma goes from 1 to n. I've got 25 I squared over n squared plus 15I over n plus 1 times 5 over n. We'll clean up the algebra there. N goes to infinity. Sigma goes from 1 to n. 5 over n times this with the distributive property is going to be 125 I squared over n cubed. 5 over n times 15I over n is 75 I over n squared, and then 5 over n. So we're going to split this up into 3 sums. I'm going to keep the I in the sum, take everything else out, and then I'll use my formulas that I just introduced a moment ago. N is still going to infinity. We've got 125 over n cubed times sigma of I squared as I goes from 1 to n. 75 over n squared. We get 5 over n, sigma of 1, as I goes from 1 to n. So we're going to use the 3 formulas for the I squared, the I, and the 1, and then we will be almost done. I've got 125 over n cubed. I squared is the long one. It was n times n plus 1 times 2n plus 1 over 6. 75 over n squared is kept. The sum of I was n times n plus 1 over 2. And then this one is just n. So now we're down to a basic limit problem. And in the interest of keeping this simple, I'm going to recognize that when n goes to infinity, the only thing that matters is the highest degree term on the top and bottom. So I'm going to take this first term and say, you know, I've got n times 2, and this is going to be 2n cubed plus stuff times 125. So this is going to be 250 n cubed plus dot 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 over 6n cubed. This is n squared times 75, 75 n squared plus stuff over 2n squared, and then 5n over n. And now as n goes to infinity, we get 250 over 6 plus 75 over 2 plus 5. There we go. And you can clean this up a little bit more. You can do, what's this going to be? 41 2/3 plus 37 1/2 plus 5. And that would be 78, 83, and 5/6. So just to kind of confirm this, I want to take that same quadratic equation and do the integral here. I'm going to write it down one more time. 0 to 5 x squared plus 3x plus 1 dx. And I want to just quickly do the reverse power rule on this. One other interpretation of integrals is as antiderivatives. So just like the power rule, you know, brought the power down, multiplied the power as a coefficient and dropped the power by 1. Another technique with integrals is you can increase the power by 1 and divide. And we'll talk about this more in detail later. But x cubed over 3, that goes up to a 3x squared over 2. That is 1x to the 0, so it becomes x to the 1 over 1. You draw this little line and do 0 to 5. And what you do is you plug in the top number here, and then subtract, plug in the bottom number, see where you land. So you get 125 over 3. 5 cubed is 125 over 3. 5 squared is 25 times 3 is 75 over 2, plus 5 over 1, and then minus, if you plug in 0, 0, 0, you obviously just get 0. So this is going to be 41 2/3 plus 37 1/2 plus 5, just like we saw a moment ago, and you can see that they do match. So we had those numbers match. 41 2/3, 37 1/2, 5 adds up to 83 5/6. So this is an introduction to using the definition of an integral to evaluate a linear and a quadratic integral. The reality is, once you get much past a quadratic, it's really not realistic to do this. So this is a good practice example, but as we get into more complicated integrals, we'll have many more tricks and shortcuts in order to evaluate those.